Okay, use the substitution. Okay, then let's use the substitution. Okay, go ahead. What should we say first?
Let me just, okay, so u squared equals e to the x minus 2. Du by dx will equal
Good. Now it's not obvious, is it? What du dx will equal? Why not?
because we've got u squared.
Yeah, but that's not necessarily a problem. We can do what?
We can square root it.
But I'd rather not, you know. We could, but this is definitely a case for what very convenient technique. Where u is an unknown function of x squared I think we ought to differentiate implicitly.
Yeah, that's what I was thinking.
Good. Go ahead.
Would you mean like, so you don't mean make it
well, instead of making u the subject of this, let's differentiate implicitly and then make dy dx the subject of what we've got down here.
So you don't just mean differentiate ex minus 2 all to the half.
No, right, but that is an alternative. Sorry, I don't mean to be, I shouldn't be dogmatic about that. I mean, if it's true, if u is e to the x minus 2 all to the power of a half, we can do that with a chain rule just as easily. Yeah, du dx. Yeah, good one then. But we'll do this as well in a minute. So differentiate that, and what have you got?
We've got a half.
Yeah.
E to the x minus 2 to the minus half times e to the x.
Yes, good. Which is, we could rewrite as e to the x over, maybe even like that. Interesting? No, not particularly. Anyway. Or in terms of u, notice. Not entirely in terms of u, but partly in terms of u. We've got that, haven't we?
Yeah.
I'm just saying, keep our options open. Any of those might be useful. Now, just reassure me you know what I meant by implicit differentiation. Differentiate both sides here with respect to x, and what do we get? Do the right-hand side first. What have we got on the right-hand side with respect to x?
E to the x.
Yeah. End of, isn't it? On the right-hand side. And what about on the left?
2u.
That's with respect to the inner function u, yes?
Then
the chain rule says
times by u.
Times by what?
I don't know.
What does the chain rule say, having differentiated with respect to the whole of the inner function? If your variable of differentiation is really further inside there, you must differentiate by, you multiply by
du dx.
du dx. After all, for all that we're frequently referring to the inner derivative, the usual statement of the chain rule is in terms of u being the inner function.
Yeah.
And you multiply by du dx. Having done dy, I mean, you could call that y. This doesn't always happen that we're able to do this. We could say dy dx now equals that bit, which is dy du, times that bit du dx. Dy dx equals dy du dx. Is that clear as mud? Have I lost you? Oh, I've lost people a few times today. Dodgy internet today. Don't think. Oh, I don't know why.
No, I'm back now. Don't worry. Don't worry.
All right, good.
Yeah.
I've got a Mozilla browser open. I don't know if that's causing problems. Nothing against Mozilla, but
I think it was my laptop.
right, fine. So here, that's differentiating implicitly, isn't it? Saying we're just going to differentiate the whole equation with respect to x using the chain rule where necessary.
Yeah.
And then notice if we make du dx the subject there, what do we get?
Well, I'm a bit confused where we're going. This.
Well, we did your differentiation here, which was great.
Yeah.
And now I'm just saying we could have done it implicitly, couldn't we? Going straight from there.
Mm.
And it is a bit more convenient. Do be aware that implicit differentiation is convenient.
Okay.
What happens? We get this. 2u du dx equals e to the x, from which we get du dx equals?
Equals e to the x over 2u.
Which is what we one version of what we recently had over here, yeah?
Yeah. Yeah.
I'm not saying it's better than that version. I'm just saying we've got this version again.
When we did the first one, how did you manage to get e to the x over 2u?
Are you clear how we managed to get e to the x over 2 times that square root?
Yeah. Well, to the minus half, that's going to be over that, and then.
Oh, hang on a minute. Well, that's right. Yes. Because you made u the subject of this, quite rightly, to get u equals this.
Yeah. No, I understand how you got the next e to the x over 2 root e to the x minus 2. From there, how have you got e to the x over 2u? Oh, 2u, because u is equal to...
U is equal to that, yeah.
Yeah, okay.
Which just didn't crop up in this process, but I'm not saying that makes this process better. But do be aware that implicit differentiation just is, well, it's great fun differentiating straight away without having to make anything the subject first.
Yeah.
Great fun, you know, pushing it a bit. Right. So are we ready to go? Can we see what we're going to substitute for what mainly? The denominator's easy enough, isn't it? We know that's going to be what?
The denominator's going to be e to the x minus, that'll just be u, that'll be u squared.
u squared. What about the numerator?
And the numerator will be let's think, we could say that's u, could we say it's u to the power of 4 plus a bunch, plus like 8 plus
Not
16.
really. It's a bit more involved than that, isn't it?
Yeah, I don't
Not
know.
sure quite what you're doing there. We do, basically we need to see it as the fourth power of e to the x.
Yeah.
So we need an expression for e to the x that we can raise to power 4, don't we?
Yeah. Yeah, I don't know. I was just trying to do it off the top of my head.
Yeah, fair enough, because I wasn't. Yeah. What are we raising to power 4?
E to the x,
Which is equal to?
which is equal to u squared plus 2.
Yes. So potentially there's quite a lot going on there that might need unpacking, and
Yeah.
we'll have to see. But we've got something to substitute for the numerator, for the denominator. Dx, have we substituted for dx yet? Not quite. Dx is going to be equal to?
Dx is equal to d is equal to, hold on, let me think, 2u du over ex.
Yeah. Again, I would rather keep the du till last.
Yeah.
Just because it's going to be a bracket, not a thing, really.
Okay.
Right.
Right.
Which is interesting. It looks as though that e to the x is going to be cancelling one of these. So that's going to be power 3 rather than 4.
Right. Okay.
Also, we still haven't done the limits. Tell you what, I'll write the integral here and write these as x values. Log 3 and log 4. Of so substituting where we can, u equals and u equals.
Why didn't we put in, oh, okay. U squared plus 2 to the 4 over u squared.
Right, should we do the limits?
Yeah.
There's no urgency, but yeah, let's do the limits.
Okay.
If x
So
is log 4, what's u?
I don't know how you do that.
So if x is log 4,
Yeah.
let's find out what u is.
Yeah, I don't know how you do e to the log 4 in your
Can
head.
you? What about 2 to the log to base 2 of 4? So maybe you're not in the habit. What if I said what's log to base 2 of 2 to the power of 4?
What are you raising 2 to get
2 raised to the power of 4.
2, 4, 8, 16. So
Which is 2 to the power of? And what have you raised 2 to get to 16?
4.
4. In other words, these are going to cancel anyway, without thinking about 16. What are we raising 2 to get 2 raised to this? Oh, well, this is what we're raising 2 to. They cancel.
Okay.
So log to base anything of that base to the power of anything, it's just like 1 to the power of 4, which is 4. Likewise, ln of e to the power of 4 equals
log base 10e.
what?
Log e.
That's natural log base e.
Yeah.
So what we're asking is, what's log base e of e to the power of 4? Well, log base e means the power we have to raise e to get. And it's just this situation again. Log base 2 of 2 to the power of anything cancels. Log base e of e to the power of anything cancels.
So it's just 4.
So it's just 4. But also it works the other way round. 2 raised to whatever the power is that we have to raise 2 to get 4 gets us 4.
Right.
E raised to whatever the power is that we have to raise e to get 4 is just 4.
I see. Okay.
All right, so you'll get used to doing that. You know, be prepared to prove it like that, although I'm rushing that terribly. I know how mind-bending logs are.
Yeah.
But with practice, you will just take it for granted that, to take another example, 3 to the power of log 3 of anything equals that thing. You'll just say, oh yeah, I know I can do that. But you do need to do a bit of thinking about it to know why, to be confident about it.
Okay.
So e to the power of a log, and indeed, if you have, say, e to the power of 2 log 3,
Yeah.
that becomes an important technique, how to get the e and the log together so that they lock, as it were, and cancel.
Yeah.
Now, how can you get that to happen there? Can you see why we can't do it yet? We haven't got the e locking with
Yeah.
the log yet.
Yeah, we still got it 2 log 3. We need to get it just log something.
So e to the log. How can we make it say e to the log of something?
Figure out what 2 log 3 is.
No. We want to express it as e to the log of what?
6.
Well, that would be nice, but that's wishful thinking without a clear reason. What is another way of writing 2 log 3? In general, what's another way of writing a log b? Well, don't forget, in the case of this one, two log 3, you could think of it as log 3 plus log 3, couldn't you?
Yeah.
Which would be log of what?
Which would be log of.
I mean, in general, what's log A plus log B? The log of.
ln AB.
Yeah. Which in this case would be log of,
9
in other words, 3
q squared.
squared.
Yeah.
Which is what we do with something like that, isn't it?
And when you've just got log like that, that means log, what do you raise 10 to get that, doesn't it?
If it said log without a base, the base is 10 by default, yes.
Yeah.
Well, where are you bringing 10 into it?
I'm just making sure that I'm not bringing 10 into it. I'm just saying that what that means, what log 3 means, is log base 10 to what you raise 10 to get 3.
No, well, this says natural log of 3, which means the
E.
power you have to raise e to
So which one
get
is
3.
10?
So natural log of 3, ln
Yeah.
of 3, means log to base e of 3. The power you have to raise e to get 3.
Isn't there one which just has a base 10? Is that log if it's just log with no
Log.
with only one number?
If it was log, unspecified log of 3, that would be read as
Right, okay.
base 10 of 3.
Okay, I see now. Yep. Okay.
So what you're trying to do in this situation is get it so that that cancels that. But it can't happen until you've got the e and the log parts to actually touch, as it were.
Yeah. Okay.
So what do we need? What can we do? How can we rewrite that? We can rewrite it as e to the power of log what?
We can rewrite it as e to the power of log 3 squared.
Yes. And then go like that.
Yeah, of course,
That's
because you can just bring
what
squared
you're
in front.
hoping
Yeah.
for. Okay, so that's a very important technique, which you'll need a lot to be able to see how to do various things. Right, where were we? We were discussing, God, it's all a bit cluttered here, isn't it? Can't see what's going on. So U was going to be what? What's U?
So U.
Oh, that's right. That's where we were. We were looking at U is the square root of ex to the minus 2, and e to the x when x is log 4. You're looking at e to the power of log 4, which is what?
E to the power of log 4 is e to the log 3 power of 4.
I've confused you with the 3 stuff, haven't I? That was a different example.
But e to the log 4. Oh, e to
the log of anything is the thing. That's all that was pertinent about what germane or something to the example.
Right.
So it's simpler than these examples. I was generalizing a bit to talk about, you know, how very useful it is to cancel an e with a log. And by the way, again, it cancels that way, but it cancels the other way as well. Not only is e to the log or a number to the equivalent log of anything does that cancel, but also the log of that base to that power, they would cancel too.
Right, okay.
Either way round. Number to the power of the log cancels. Log of that number raised to whatever power also cancels.
I see, okay.
So when x equals log 4, e to the x equals
when x equals 4, e to the x equals 4.
yes, and therefore u squared equals
U squared equals 2.
and therefore
No,
u equals
U equals 2, doesn't it?
yeah.
Yeah.
Okay. When x is log 3, e to the x is
E to the x equals 3
so u squared equals
equals root 3. No. Wait, u squared equals 3. So u will equal root
does u
3.
squared equal 3? I don't think we said that.
Oh, what did we say? Ex minus, okay, so 3 minus 2 equals 1, root 1.
Yes. So the lower limit is,
Root 1.
and this time they don't need switching round because root 2 is higher than 1.
Yeah.
Right. So we've
And
done
then
the limits.
we have u squared plus 2 all to the 4 over u squared, won't we?
Right.
After
Hang on a
looking.
sec. You're saying what we've got here. Oh, what we've got here is e to the 4x is going to be what? Or shall we leave it as e to the 4x for a moment and deal with it in a while? I mean, can you see why I'm saying that?
No.
It's because I noticed, having failed to notice previously, I later on noticed that this is going to probably end up being power 3 instead of power 4 here. Here.
Okay. Oh.
Nonetheless, underneath, we could substitute e to the x minus 2 for what? What could we write instead of e to the x minus 2?
U squared.
Yes. And what could we write instead of dx, apparently?
2u over ex du.
Yeah. Don't forget the time sign.
E to the 4x. Yeah.
So things are simplifying a bit here. I don't have to mention the u's anymore, but do notice that we've changed the limits. If it's a definite integral, you don't substitute back. More than once you've been anxious to substitute back to the original variable. That only happens if it's an indefinite integral. If it's a definite integral, you're going to get numbers at the end, not a function of whatever. So it doesn't matter what it's a function of. You're just going to get numbers. From 1 to root 2 of, okay, simplifying this a little bit.
We could say e to the 3x.
Yes. Carry on.
Over u squared still. Oh no, we've got 2u. Okay, I didn't realize we can just say over u times 2.
Then times 2, good. Du. And now what? Well, the e to the 3x
will just become u squared plus 2 to the 3.
Yes. Okay, which does need unpacking, otherwise we don't know. Oh, yeah, we're using the substitution we were told to use, so fine. So yes, we've got to work with this one. And what next?
Now we integrate.
Can you integrate that already? Is it in a fit condition to integrate?
Not. You say 2u. Oh no. 2 over u. I don't know. Can we say 2? Oh no. I can't. We're doing multiply out u squared plus 2.
The thing is, you notice here, it's not, you know, it's going to be an easy integration, relatively speaking. There's not, I mean, there's hardly any chain rule, if any. Because we're going to turn it into a polynomial, just powers of u.
Yeah.
So we just have to go through that process. Looks a bit tedious. But if we say 2 times, what cubic then?
U.
By the way, to make it slightly less tedious than necessary, shall we recall how a plus b cubed expands?
You could use the.
Remind me first how a plus b squared, all squared, expands.
A squared plus 2ab plus b squared.
Now, thinking of that,
yeah,
1, 2, 1 in Pascal's triangle.
Yeah, then it'll be 1, 3, 3, 1.
Yes. So this is
a cubed plus ab 3ab plus 3ba.
Don't forget
3a squared b plus 3b squared a, or ab squared.
Yes.
Plus b cubed.
Yes, exactly so. So using that template, what do we get here?
We get 2 times
and then inside. So notice that I've used a 2. You know, I'm setting out one large pair of brackets for all of that.
Oh, yeah.
Outside it. So be aware of that.
U to the 6.
Yeah.
Plus 3.
Yeah.
U to the 4.
But then times
2.
So how many u to the 4 is it in fact?
6.
Good. Next term?
Plus 4 times 3 equals 12u squared.
Yes, good.
Plus 8.
Yes. All over you. Do you?
Then times the 2 through probably.
Yeah, but also divide by u. Why not? Otherwise. So let's, you know, we can be rid of the fraction now, can't we? We can say we've got 2u to the power of what?
5.
Plus?
Plus 12u to the 3.
To the 3, yeah? Good.
Plus 24u plus 8 over u.
Don't forget the 2.
Oh, no, 16 over u, sorry.
16 over u. All with respect to u. And now we can do an antiderivative between those 2 limits.
Yes.
So, in turn,
Then we'd have u to the 10 over 10.
sorry,
Oh, sorry, I'm being stupid. Wait, 2u to the 5, that would integrate to 2 to the 6, that would be a third u to the 6.
good,
No, what I was doing at first.
good, good.
A third u to the 6 plus u to the 4, 12 over 4 equals 3u to the 4
Good.
plus 12u squared
Good.
plus ln 16.
Pardon? That came out wrong.
16 ln
Of,
u.
yes.
Okay.
Okay, giving. For the root
Giving.
2's, we get what?
You get a third of root 2 to the power of 6.
Yeah, what's root 2 to the power of 6?
2 to the power of 5.
Careful, no. It's not. How are you thinking that?
Root 2, so
What we're asking is root 2 to the power of 6, which is 2 to the power of a half to the power of 6.
okay, so it's 2 to the power of 6 over 2, which is 2 what is root 2? I don't even know what root 2 is.
You don't have to.
Root 2 times 6. Not root 2 times 6, root 2.
What's the next thing you said after this? You said it was going to be 2 to the power of what?
6 over 2, which is the same as 3 over 1.
Yes.
So that's the same as 3.
Yeah.
So 2, 4, 8. A
Yes.
third times 8
Exactly.
equals 8 over 3.
Good. So first term, 8 over 3.
Plus
Next term?
root 2 to the 4 is 2 to the 4 over 2, 2 to the 2 is 4, 3 times 4 equals 12.
Good.
Plus 2 to the 2, 24.
Good. Plus?
That's 16 ln u ln root 2 is ln root 2 to the power of 16.
Oh, nice idea in a way. We might have to backtrack slightly, but I take your point. So you're at that stage, you're writing that as ln of root 2 to the power of 16, which you can simplify as 2 to the power of what?
8.
Yes.
Ln 2 to the power of 8. Yeah.
Yeah, good. Followed by the one versions.
Followed by 1 to the power of 6 equals 1. 1 times a third equals a third.
Yeah, but you're not mentioning. What am I writing?
Oh, plus a third.
Really?
Minus a third.
Yeah, we're subtracting all of these.
Yeah, I write this bit out differently to you. That's
Okay. Yeah. Yeah, that's fair enough. Well, yeah, as long as you've got a minus sign somewhere.
yeah.
Okay.
Then 3 plus 3.
Yeah.
Minus 3 in your case.
Yes. This sounds a bit.
And then
Yeah.
1 squared 12 plus 12 plus
Oh yeah, I'm with you.
plus ln 1, which is
Remember,
0.
which is 0. So
Yeah.
the whole term is 0 there. Okay. So the 12s cancel. We've got 7 thirds plus 21.
How have you done ln 2 to the power of 8 in your head?
I haven't.
Oh.
But I'm going to write it as, I would rather write it how? Ln to the power of, sorry, ln of 2 to the 8. Rather than writing ln of 256, I'm going to write what?
What, just, do you mean what is 2 to the 8?
Well, 2 to the 8 is 256, but I'm not going to write ln of 256. I'm going to write how many log 2?
How many log 2? 8 log 2.
Yeah. That's just looks nicer than log of 256. So that's 63 thirds plus another 7 makes 70 thirds plus 8 log 2. We hope.
Yeah.
Which one was it?
Number 6.
Oh, I see.
Yeah.
Yeah, yes, it does look like it's in the right format. So chances are, let's check.
Yeah,
You
so
don't have access to this resource. Bloody cheap. I do as well.
I'll find out. 11E.
Well, I do have access though. I think it's just the lag because I haven't been, I was logged out or something.
Wait, what number was it? 6.
What page were we on? 3?
We got
7.
it right. You got it right.
Good.
Yeah.
Right.
Yeah.
Okay.
So it's
Okay.
8.
Which one? 8? Did you say?
Well, yeah, yeah.
Yeah, we've got time. I mean, what with delays and I've had a lot. I keep being thrown off the internet today. Anyway, this. So which one? Sorry.
Yeah, should we do 8? Yeah.
Okay. Hint: use exact trigonometric values to change the limits. Yeah.
Where have you read that? Oh, right, yeah. There.
Well, it is saying use the substitution. Okay, if we must. Yeah, because you do need to practice at just when you must. Yes, that's true. Right.
80. U equals cos x. Okay, so
yeah. Okay, so you're going with that. Yeah.
du dx will equal minus sin x.
Yep.
And then dx will equal 1 over minus 1 over sin x du.
Yep.
And then we could say we've got put the u's in? Not yet, or I don't
Sorry?
know. Would you not put the u's in yet?
Well, yeah, as far as we can.
Yeah.
Then what do we get?
So then we get sine 3x u
Find 3x if you mean.
sine cubed x.
Yeah.
U squared.
Yeah.
Minus times minus
Times minus, good.
minus 1 over sine x du.
Yeah, that's fine. And we don't have to be desperate to substitute every single option, which I think perhaps I have on occasion suggested.
Okay, well, since we know that
The only thing about the limits is you ought to be clear which one it is. If you're leaving them as x values, let's be clear about that.
so oh yeah, leave them as x values for now. And then let's see, so to get sine x cubed, could we say,
All right, but in that case, you're missing the benefit you've already got by.
oh yeah, of course, so we could cancel the cubed and put a squared.
Yeah.
Okay, so then we could say sine squared x, sine x squared times u squared times minus du.
Well, yeah, you don't want to say minus times minus, do you? You maybe bring the minus sign around the front like that.
Yeah.
Or even outside the integral. And then what?
Then we could say, so sine squared x equals 1 minus cos squared x, which would equal.
In which case, I think, unless you're going to call it cos squared minus 1 for the
1 minus u squared.
Sorry, say again?
Can't we just say 1 minus u squared?
Yeah, yes, indeed. I'm just saying be careful of the minus sign here.
Oh, where was the minus sign come from?
Well, where was yours?
Mine was in front of the whole.
Oh, in front of the integral. You've taken it outside the integral. That's great. Let's leave it there then, and it's not a problem. Good. Are you still giving these as x values? In which case, I think you ought to be explicit about it.
Yeah, I have for now, yeah.
And then you're replacing sine squared with a bracketed expression like so.
Yeah.
Oh, and in the process, you were saying I'm going to call that u squared, which is quite good idea.
Yeah, okay. 1 minus u squared du. Then we would say that is u squared minus u to the 4.
All right. Are you taking the integral sign for granted and the minus sign for granted?
Yeah.
Yeah. Pretend I need to be dictation. You know, I need to be told
everything.
Yes.
Yeah, we'll leave that for now, then the integral sign.
Oh, all right. You're just saying, okay. So as before, you could say, integral sign as before, it's minus integral from this x value to that x value But now inside, you're going to say x to the 4, I beg your pardon, x squared minus x to the 4, were you saying?
Yeah. And then we probably change the integral sign now
How?
by saying pi over 3 u, when u equals pi over 3.
No, that doesn't quite make sense.
So x equals pi over 3.
If x equals pi over 3, then
u equals cos 60
yes,
equals,
what time on the clock?
which is 1,
And therefore has a cos coordinate of,
has a cos coordinate of 1 root 2. God, I can never do these in my head.
well, hang on, you shouldn't be doing anything apart from thinking the cos coordinate is which coordinate always?
The x-axis.
Right, so you're just looking for the x coordinate of 1 o'clock, but are you remembering there's a nice equilateral triangle between 1 o'clock and 3 o'clock and the center of the clock?
So it's 1, 2, 3, isn't it? Not 1, 2, 3. 1, 1, and then the hypotenuse is 2.
Yes.
So 0.5.
Yes, it's that simple.
Yeah.
Yeah, just look, think about the equilateral there, and you're halfway across it.
Yeah.
Right, so the cos value of that upper limit is a half, and
Yeah.
that's your u value then.
Yeah.
Okay, and the lower value of x?
0.
Giving
So
a u value of
1.
1, right. Now notice, these need switching, don't they? Or somebody will get confused, not necessarily you, but we like to have the later x value.
It's minus, so we can just flip it.
So we can just flip it and cancel that minus, indeed, yes.
Of u squared minus u to the 4 du, then we will square bracket. No, it's u squared minus u. No, it's the other way around, isn't it?
Yes. Thank you. Oh. Right, and that should come out beautifully, does it? So we get a third u cubed minus a fifth u to the 5 between those limits. And let's see if we agree on the numbers too. So a third minus a fifth minus a 24th, and then plus 160th is going to be a third of 480 is 160, a fifth of 480 is 98, 6. Minus 20 and plus 3 over 480.
Yeah, 17 over, yeah.
So taking away, sorry, 116, that's 44, 47
20.
over 480. Oh, and that's what they told us, is it?
Where
Yeah.
have I gone then? Was that the right answer?
Yeah.
I've done it wrong then.
Which bit? I've got these fractions. You were kind of worrying me. Well, no, I mean, maybe it's just that you're writing it a different way, but obviously the thing to be careful of is
I'm confused.
making sure you're subtracting all of these from all of them. Which is why I've got a minus there and a plus there, and I wonder if you have too.
Yeah. Okay, good. Done it.
Okay.
Okay. Well, cheers,
Cool.
Tom.
All right. I'll send you that.